Hello there and welcome to this video on centripetal force. Now, centripetal force acts on corners. It acts as you turn around. So one great big corner, some infinitely lasting corner, is a circle. So let's use that as an example. So we'll start off here at the end of this red arrow and we'll say that we've got a moon. We've got a great big mass, a moon orbiting a planet. Now let me ask you this. What would happen if I were to click my fingers and all the forces acting on that moon were to disappear? No more force acting on that moon. Well, in accordance with Isaac Newton's laws, it would carry on in a straight line forever. In order to change something's motion, change something's direction or magnitude of motion, you're going to need an unbalanced force. You're going to need a net force, and we haven't got one, so it would go on forever. Now, I don't want it to go on forever. I want it to carry on going around and around and around. So how do I do that? Well, I do that by changing the red arrow into this blue arrow, changing this velocity vector into this one. How do I do that? We've got this nice little closed diagram here. We're going to change the red original velocity vector into this final velocity vector. And the way you do that is this. This black arrow here, that is the change in velocity that is required to do that. You want to turn that into that, you're going to need a change in velocity of that size and magnitude and that direction. And if I paste this over here, we can see it's towards the center. So if I want my moon to continue going round, I have to change it from this direction into this direction, and the way you do that is to have a velocity in this direction. So I'm going to need a force. I'm going to need a force that's pushing my moon in this direction towards the center if I want it to turn around this corner. Okay, so moving on to the next stage. Now I don't want it flying off into the universe. I want it turning into this next velocity vector, and again the way I'm going to do that is by adding another velocity vector towards the center. And I need that force pushing that inwards. I need a constant force pushing towards the center of the circle to set up these velocities, change in velocity vectors, which will continue to turn these arrows round. And if I continue this, the next velocity vector, how would I get it to change? Well, there'd be an arrow pointing towards the middle and lots of arrows pointing towards the middle. So, to summarize, if I want my moon to continue orbiting in this circle, I'm going to have to continually apply a force towards the center. And that force towards the center we call centripetal force. Without it, it would carry on in a straight line. So here we are. Here's our planet going around. Here's our centripetal force pushing in towards the center. So here you can see what these guys are doing here is they are continually providing that inward centripetal force required to keep the thing going round and round and round, so that he's changing that velocity vector constantly over and over again, and when he stops it carries off in a straight line. So this lady swinging this bucket around her head, she has to be providing an inwards force. She's pulling that string towards the center in order to make that bucket carry on round. So let's do a little thought experiment. If we had a little tiny man and we shrunk him down and we put him in this bucket and he was being swung around that lady's head, what would we see? Well, we know that the bottom of this bucket must be accelerating inwards. The bottom of this bucket is accelerating inwards. It has to be. We know there's a force acting on it. That's called centripetal force, the one we've been talking about, and that force is acting on a mass, the bucket, the bottom of this bucket, and so therefore that force has an acceleration. F equals ma, force is mass times acceleration. If you have a force acting on a mass, then it is accelerating. Now the bottom of this bucket and this man, they're all accelerating towards the center of the circle, and that sounds kind of odd because we know acceleration is sort of, a car doing 0 to 60 in however many seconds, getting faster and faster and faster. You don't have to be changing speed in order to be accelerating. You can be changing direction as well. Something that's going round and round in a circle is constantly accelerating. So what I'm telling you is this bucket, the bottom of this bucket, is accelerating inwards. Now let's imagine that now you're this guy you're in the bucket. What would that feel like? What would you feel? Well, you'd feel the floor coming up towards you. On your feet, you would feel the floor coming up towards you. So that would feel to you as if you were pushing down on the floor. It would feel just like gravity. And what we can do is we can simulate this. We can simulate artificial gravity by spinning you around. So the floor is, what's actually happened is the floor is constantly accelerating towards you, but it feels like you're being pushed down to the floor. And that's actually a trick. It's actually a problem of perspective. It's called an inertial frame of reference. You have an inertial frame of reference. There's no such thing as centrifugal force, but it feels like there should be if you're the one in the bucket in this instance. So you can simulate artificial gravity like this, and that's been known about for a while, and people have sort of speculated, and science fiction films have come up with things like Stanley Kubrick's 2001 Space Odyssey, this idea of a spinning space station in which you could simulate gravity. And if you spin it at the right speed, at the right velocity, the right revolutions per second, per minute, whatever, then you can get it to 9.81, which is the strength of gravity, 9.81 newtons per kilo. So in fact, if you could spin it faster, you could make gravity increase. If you spun it slower, you could make it decrease. So you can simulate artificial gravity using this principle. Let's have a look at one last example of centripetal force. Here we are, car going round a corner. When the car goes around the corner, it's the tyres that provide this centripetal force. It's the tyres that are pushing inwards towards the centre. Now, what's going to happen if your tyres suddenly become incapable of providing that force? Well, just like that moon, I said, if you were going to switch off gravity, what happened to that moon? Well, it flew off in a straight line. And if your tyres suddenly become unable to provide that centripetal inwards force, they break traction, in other words, your car is going to skid off in a straight line and into the bushes. So there we are. That's a quick run through of centripetal force. So quick summary. If you want something to go round, you have to constantly change that velocity vector. And in order to do that, you have to provide a constant inwards force. We call that inwards force centripetal force. Now it can kind of feel, because of an inertial frame of reference, like the guy in the bucket. If you're the one in the bucket, it can feel like you're being pushed down, but you're not. What's actually happening is the floor is coming up towards you. The floor is accelerating constantly towards you. It's quite a difficult thing to get your head around. But that's the idea of centrifugal force. Some physicists get a bit upset when you talk about centrifugal force because it's not really such a thing. It's just a perspective thing. Okay, so there we go. That's a quick run through of centripetal force. Thanks for watching.